Good morning, dear students. This is the second lecture. The title of this lecture is Some More OR Models, and in this lecture we will try to model some more real life problems in terms of a linear programming model. Before I do that, let us recapitulate what we did in the previous lecture. In the previous lecture, we defined what is the mathematical definition of a linear programming problem, and we defined what are the decision variables, what are the constraints that are imposed on the decision variables, what is the objective function, and so on. This we did with the help of a couple of examples. So, today in this lecture we will look at some more real life problems which occur commonly in our day to day activities. I will be covering the following 5 types of problems which occur in our real life problems. The first problem is the transportation problem. The second one is the traveling salesman problem. The third one is the capital budgeting problem. Fourth, cargo loading problem, and the fifth one is the caterer problem. After this, there will be some questions and some exercises for you to do later on. Let us look at the first problem, which is the transportation problem. Now, in this problem, let us look at, suppose there is an example where certain amount of goods have to be transported from a number of sources to a number of destinations. So, there are, let us suppose 1, 2, 3, 4 many sources, and there are similarly many destinations 1, 2, 3, 4 many destinations. So, from each of the source, let us say a commodity has to be transported to each of the destinations, and let us suppose, for example, the first source, the cost of transportation of that goods to the various destinations is given to us. Cost per unit of the commodity is given to us, and like this all this information for all the sources and all the destinations is given. So, the problem can be represented in a tabular form as shown in this table, where we have the sources on the first column and the destination on the top row. So, you can see that each commodity can be transformed from the source, from the ith source to the jth destination, and these are the costs that are given. So, for example, from the first origin, the cost of transporting the good to the first destination is given by this constant 1. Similarly, from the first origin to the second destination is given by 2. So, like this, the cost of transporting the good from each of the origin to each of the destination is given in this table. Now, the transportation problem says that we need to determine how many units of the commodity should be transported from the ith origin to the jth destination in such a way that the cost, that is the overall cost, is minimum. So, that means we need to formulate the objective function, and we need to look at the decision variables, and before we do that we need to look at what are the supplies that are available at each of the origins. This is given in the rightmost column, that is the supply at the origin 1 is given to be 70 and like this. Similarly, the availability at the destinations. So, this is given in the last row. So, like this entire table represents the data for the modeling of the transportation problem. This is the model. Let us look at it carefully what it means. Xij is the number of units to be transported from the ith source to the jth destination. As you remember, in the last lecture we had defined 3 steps to model a given problem. So, this is the first step, that is we want to define the decision variables. So, Xij are the decision variables indicating the number of units to be transported from the ith source to the jth destination. And obviously, all these Xij's should be greater than or equal to 0, and they should also be integers because they are number. So, you cannot transport, let us say 2.3 units, you can either transport 2 or 3. So, the Xij's should be greater than or equal to 0 and they should be integers. The next step is to identify the objective function, and in this case the objective function is minimization of x11 plus 2 times x12 etc. Now, how did these coefficients come? Let us go back to the previous slide and look at the entries in the first row of the table, and you will see that on the first row of the table the coefficient 1 corresponds to the x11 entry. So, x11 multiplied by 1 is the first entry in the objective function. Similarly, the second entry in the first row is 2. So, x12 should be multiplied by 2, that is why it says 2 times x12 and like this. So, the entire expression for the objective function can be obtained like this, and this is the overall cost that has to be minimized. Now, also this has to be subject to the following constraints, that is x11, x12 plus x13 plus x14 is equal to 70. This is coming from the first row. So, here you look at this first row 1, 2, minus 2, 3, these are the coefficients of x11, x12, x13, x14, and since the supply is 70, so we need to restrict this first equation as x11 plus x12 plus x13 plus x14 is equal to 70, and in this way the other 2 equations corresponding to the other rows also comes into existence. Also, we need to look at the vertical constraints. So, the vertical constraints tells us x11 plus x21 plus x31 is equal to 40. This comes from the first column. So, here look at the first column. In the first column the availability is given by, the demand is given by 1 times x11, 2 times x21 and 1 times x31. So, this demand is equal to 40, that is why this equation comes, and similarly for the other 2 columns the demand has to be met and therefore, we get these 3 equations, and as I said before, all the Xij's should be greater than or equal to 0 and they should be integers. So, this is the transportation problem which is found to be occurring in a number of places. The second problem that I am going to discuss is called the traveling salesman's problem. This is also a problem which occurs in our day to day lives, and the problem states that there is a salesman who has to go to a number of cities, he has to visit a number of cities in such a way that he starts from the first city and moves to the other cities once and only once. He has to travel each of the cities once and only once in such a way that he returns back to the city number 1, because he is supposed to sell his product. So, the salesman has to visit, let us say 5 number of cities in this example, and these cities are called C1, C2, etc. He should start from the city number C1 and he has to move to all the cities in such a way that he visits each of the city once and only once, and finally returns back to the city number 1. Now, the cost of travelling from city Ci to city Cj is given to us. This is given in terms of, let us say, rupees or some units. The journey that he has to perform should be in such a way that the cost of travelling from each of the cities and returning back to the first city should be minimum. So, with this in mind, we need to model this problem as a linear programming problem. Now, this is the data that is given in the problem. You will note that the diagonal elements in this matrix are marked with a dash, indicating that there is no point of travelling from C1 to C1. Similarly, there is no point of travelling from C2 to C2. That is the reason why the diagonal entries are blank. Also, you will observe that there is no entry corresponding to C5 to C1 and similarly C1 to C5. The reason is that there is no connections between the city C1 and the city C5. So, that is the reason why this is left as a blank entry. You will also observe that it is not necessary that this is a symmetric matrix, that is the lower and the upper triangular matrix need not be same in general. The reason is that, for example, a C21, the entry C21 is not equal to the entry C12. The reason is that suppose you are travelling from one city to another city, the cost of travelling from the first city to the second need not be the same as the cost for travelling from C2 to C1. So, that is the reason why it is not necessary that Cij is equal to Cji. Now, looking at this cost matrix, we need to design the problem in such a way that the cost is minimum. So, here Xij, this is the first step, that is identification of the decision variables. Xij are the decisions variables and it takes the value 1 if the salesman travels from city I to city j, and it takes the value 0 otherwise. So, these type of problems are called 0-1 programming problems. That is, in this is a specialized kind of a problem where the decision parameters, they take only 2 types of values, either 1 or 0. So, here also Xij takes value 1 if the salesman travels from city I to city j, and it takes value 0 otherwise. Now, again as before, the second step is to identify the objective function, and the objective function can be obtained by this expression 20 times x12. Please note that there is no entry corresponding to x11 because the matrix, in the matrix there was a dash, there was a dash entry in the x11 column. So, that is the reason why we will start with x12. So, 20 times x12, 4 times x13, look at the table, 4 times x13 and like that, 15 times x14, etc. So, the entire expression for the objective function can be obtained like this. Apart from this, we also have another constraint of this type, that is summation of xij is equal to 1 for all I and j varying from 1 to up to 5. Similarly, summation xij is equal to 1 for all j and I varying from 1, 2, 3, 4 up to 5. What does this mean? This means that corresponding to this table, we want that all the xij's in the horizontal and in the vertical rows should sum up to 1, and that is the reason why we need to impose these constraints. Next is the capital budgeting problem. Now, this is a very interesting problem and it is as follows, that is Remco Industries is in the process of drawing up a capital budget for the level for the next coming 3 years. It has funds to the tune of rupees 1 lakh which can be allocated to projects A, B, C and D. The net cash flow associated with an investment of rupees 1 in each project is given below. Now, here is a table, the data is given in this table. It tells us that if you look at the A, B, C, D, E and you look at what kind of levels it has 0, 0 is the present level. Similarly, 1 is the level after 1 year, the level 2 is the level after 2 years and 3 is the level after 3 years. So, this is the data in terms of rupees that is given to us and we need to formulate it as a linear programming problem. So, this means that rupee 1 invested in the investment B requires rupees 1 cash flow at time 1 and returns 0.5 at time 2 and rupees 1 at time 3. Now, to ensure that the firm remains reasonably diversified, the firm will not commit an investment exceeding rupees 75,000 in any project. The firm cannot borrow funds, therefore, the cash available for investment at any time is limited to cash on hand. The firm will earn interests at the rate of 8% per annum by parking the uninvested funds in money market investments. Assume that the returns from investments can be immediately reinvested, that is the positive cash flow received from project C at time 1 can immediately be reinvested in project B. We need to formulate the problem as a linear programming problem so that the maximum cash flow on hand at time 3 is obtained. So, we need to look at a couple of observations. The first one is that the company wants to decide the optimum allocation of funds to the projects A, B, C, D, E and money market investments. So, therefore, let us look at the first step. The first step is the decision variables. So, the decision variables can be identified as XA, XB, XC, XD and XE be the amount in rupees invested in the projects A, B, C, D and E. So, that is the first part. We have identified the decision variables XA, XB, XC, XD and XE. S0, S1 and S2 be the surplus amount at year number 0, 1, 2, which is the amount invested in money market. So, this is the surplus amount which has to be invested in the money market. Now, the objective function is to maximize the cash on hand at time 3. So, let us look at the various levels. At the first level, what is the situation? At the second level, what is the situation? So, at the first level, that is at the 0 level, the funds available is rupees 1 lakh, this is given in the problem. So, the funds available is 1 lakh and the amount that is invested is given by x a plus x c plus x d. Therefore, what is S0? What is S0? S0 is the difference of the two, that is 1 lakh minus x a plus x c plus x d. So, this is the S0. Next comes the level 1. At level 1, the funds that are available are as follows, that is rupees 0.5 x a plus 1.2 x c and so on. Also, the amount that is invested is x b. So, therefore, we have a constraint, that is x b should be less than equal to 0.5 x a plus 1.2 x c and so on. And what is the surplus? Again, at this level the surplus is S1, which is given by the difference of the two. So, just as we got the surplus amount in level 0, we have got the surplus amount at level 1. Now, let us come to the level 2. In the level 2, the funds available are rupees x a plus 0.5 x b and so on, and the amount invested is x e. So, therefore, we have a constraint that the amount invested should be less than equal to the funds that is available, because you cannot invest more than what is available. Therefore, again as before, we will calculate the surplus amount. The surplus amount is given by S2, which is equal to the difference of the amount that is invested and the amount that is available. Therefore, at level 3, that is after the third year, the funds that are available are as follows, rupees x b plus 1.9 x d and so on. So, like this we have obtained the mathematical model in terms of a linear programming problem for this investment problem. Therefore, in a nutshell we can write down the final model as follows: the objective function and the constraints in terms of the S1, S2 and S3. Also please note that x a, x b, x c, x d, they should all be less than equal to 75,000, and also each of the decision variables as well as S1, S2, S3, they should be all greater than or equal to 0. Next comes another interesting problem, which is called as the cargo loading problem. Now, there is a cargo has to be loaded by some units of some commodity. Now, how this problem can be modeled as a linear programming problem, we will see in this example. There is a 4-ton vessel to be loaded with one or more of 3 items. So, there are 3 items, either one or more of the 3 items have to be loaded. The following table gives the unit weight Wi in tons and the unit revenues RIs in thousands of rupees for the item corresponding to I. Now, the problem is how should the vessel be loaded to maximize the total return? That is the problem. How should the vessel be loaded so as to maximize the total return. Now, here is the data that is given for the problem, that is the items are numbered as 1, 2 and 3 and the corresponding Wi is given to be 2, 3 and 1 and the corresponding Ri is given to be 31, 47 and 14. So, as before we need to look at what are the decision variables, what are the objective functions, what are the constraints. So, let us define the decision variables as follows. U1, U2 and U3 are the number of units of types I is equal to 1, 2 and 3 which should be loaded on the vessel to maximize the total return. Remember, we have to maximize the total return, and the objective function therefore looks like this: maximization of z is equal to 31 times u1. Where did this 31 come from? Let us see. Here it is on the last column, 31 times u1 plus 47 times u2 and 14 times u3. So, that is the return, and this has to be subject to the condition 2 times u1. Where did this 2 come from? This came from the data that is given in the table under the Wi column. So, 2 times u1 plus 3 times u2 plus u3 should be less than or equal to 4. And of course, as before, all the parameters u1, u2 and u3 should be non-negative integers, that is they should be greater than or equal to 0 and they should be integers. The last example of this lecture is the Caterer problem. This problem occurs in a number of situations where in hotel management a caterer has to provide fresh napkins to his customer. So, let us look at the problem. The problem says that a caterer has to organize a garden party for a week, and for each of the 7 days of the week he knows the amount of napkins that he has to provide to his customers. So, he needs a total of 160, 120, 80, 90, 110, 100 and 120 fresh napkins during all the 7 days of the week. Each new napkin costs him rupees 3. He can use the soiled napkins after getting them washed from a laundry. Ordinarily, washing charges are 0.60 per napkin and they are returned after 4 days. However, the laundry also provides an express service at a cost of rupees 1 per napkin, and in which case they are returned after 2 days. So, there are two ways of getting the soiled napkins cleaned, either in the ordinary way, that is it will cost him 60 paisa and it will be returned after 4 days, and the second way is to get a express service where the cost will be rupees 1 per napkin and it will be returned after 2 days. Now, we are required to formulate this problem as an LP problem in order to determine the planning schedule of the caterer, so that he should adopt to buy or sell and send the napkins to the laundry so as to minimize the cost. So, as before, the first step is the identification of the decision variables. Xj is the number of napkins bought on the jth day. So, there are x1, x2, x3, x4, x5, x6 and x7. So, these are 7 parameters corresponding to each of the 7 days of the week. Also we have Yj is defined as the number of napkins sent for express laundry services on the jth day, and similarly we have Zj equal to the number of napkins sent for ordinary laundry services on the jth day, and also we have Vj as the number of napkins soiled on the jth day, but not sent to laundry on the jth day. So, we have 7 Xi's, 7 Yi's and 7 Zi's, and of course, you do not know how many of them will be Vi's. All these decision parameters, that is Xi's, Yi's, Zi's and Vi's, they should be greater than or equal to 0 and they should be integers. Now, let us look at what happens during each of the days. So, for the first 3 days he has to buy new napkins because no napkins are available. So, therefore, for the first 3 days he has to buy new napkins. Therefore, x1 should be equal to 160, x2 should be equal to 120 and x3 should be equal to 60. These are the number of napkins he has to buy. The supply of napkins for the 7 days can be shown in the form of this table. Now, let us look at this table, what it means. For each of the 7 days, this data shows how many napkins are available to him, how many napkins he has to send to the ordinary way of the laundry and how many napkins he has to send to the express laundry. And like this, the last row also tells us the total, that is his requirement, the total requirement. So, this table depicts the entire situation of the napkins that he is going to send for laundry, either the ordinary service or the express service. Therefore, the constraints can be modeled like this in terms of x1 is equal to 160, x2 is equal to 120, x3 is equal to 60, x4 plus y1 is equal to 90 and so on. So, each of these constraint is coming from this table that we have formulated over here, which shows how many number of napkins have to be sent for the ordinary laundry service and how many napkins have to be sent for express service. So, these are all the 7 constraints for each of the 7 days. Now, the number of dirty napkins on the jth day is equal to the number of used napkins on the jth day plus the number of napkins left on the j minus 1th day. So, therefore, we can write the corresponding constraints for each of the 7 days as follows, that is y1 plus z1 plus v1 is equal to 160, y2 plus z2 plus v2 is equal to 120 plus v1, y3 plus z3 plus v3 is equal to 60 plus v2, y4 plus z4 plus v4 is equal to 90 plus v3, y5 plus z5 plus v5 is equal to 110 plus v4, y6 plus z6 plus v6 is equal to 100 plus v5, y7 plus z7 plus v7 is equal to 120 plus v6. So, these are the constraints corresponding to each of the 7 days of the week, but we find that some of the y's are zeros and some of the z's are 0. So, therefore, if you substitute these conditions back into those previous equations, Finally, we get this set of equations. So, you can please check this how we can substitute the values of these y's and these z's which are 0 back into the equation on the previous slide. So, here you have to substitute those values of y's and z's as zeros, and now you get this system of equations as the equality constraints of the linear programming problem. And what about the objective function? Now, the objective function is to minimize this expression z is equal to 3 times x1 plus x2 plus x3 plus x4 plus x5 plus x6 plus x7 plus y1 plus y2 plus y3 plus y4 plus 0.6 times z1 plus z2 plus z3. Now, you can very well judge how this expression has come. This expression has come from the data that is given into the problem, that is the cost of the napkins. The first part of this expression where we are multiplying x1, x2 etc. by 3 is because the cost of the napkin is 3 rupees. So, therefore, each of the x1, x2 etc. has to be multiplied by 3. Next comes y1, y2. This is to be multiplied by 1 because the cost of the express service is 1. Similarly, the cost of the ordinary service of laundry is 60 paisa. So, therefore, it has to be multiplied by 0.6. So, that completes this lecture, and now I would like to give you an exercise for you to solve and for you to write the linear programming model corresponding to this problem. The problem is as follows: a lady of taste and fashion has the following requirement of sarees for 6 months. Each saree costs rupees 500 and once worn can be repeated, but not in the same or in the next month. It can be worn again in the 3rd, 4th, 5th and 6th month, but at an estimated cost of rupees 100, 80, 60 and 50 respectively, which includes the dry cleaning charges and also the cost of the loss of face to the lady. All the sarees have to be rejected after August, as they would be out of fashion next year. Find the schedule of purchasing and washing the sarees so that the cost is minimum. So, this table is given to you as the data, and you are required to model this problem as a linear programming problem. Let me repeat, you have to write down the 3 steps of the problem, that is, you have to write down the decision variables, you have to identify the objective function, you have to identify the constraints, and you have also to identify what are the conditions that you have to impose on the decision parameters. So, wish you all the best and do keep in touch. Thank you.